All right. Hi, everyone. Welcome to Confluent at the Edge on AWS. So we're thrilled to have you in this session today. I know there are many different ways to spend your time at reInvent, and I just wanted to acknowledge how grateful we are to have you here with us. I'm Joseph Monais, Staff Cloud Partner Solutions Architect at Confluent, and joining me today is Justin Lee, one of our outstanding staff solution engineers.
How's it going? Nice to meet everybody. Good to be here.
We're going to discuss data in motion at the edge. There'll be some joy, plenty of insight, and hopefully some fun. So just a quick summary of what we're going to be diving into today. First, we'll do a quick dive into what Apache Kafka is and the rise of data in motion. We'll then discuss who is Confluent and how do we relate to Kafka. What do we mean by edge and common challenges in these architecture patterns? Then we will explore AWS and Confluent technologies that make working at the edge easier. We'll close today with a discussion of some common edge use cases, a live demonstration of data in motion, and if time permits, some Q&A. Buckle up. So at its core, Apache Kafka is a scalable, highly available event streaming platform, which you could think of as the central nervous system of an enterprise. Kafka also makes it easier to get more value out of your existing systems and to make them real-time, so to speak. And I say real-time, so to speak, because it depends on your definition of real-time. Kafka, we're talking 20 to 30 milliseconds. Some people have those absolute 0 millisecond use cases, not exactly a Kafka fit. We now like to focus on a new paradigm called data in motion, which is centered around event streams and streaming analytics and processing. Here, data is not static and at rest, but continuously evolving and continuously being processed and analyzed in real time. In today's world, the fundamental notion is that data is moving, not sitting at rest. We'll show an example of this in our demo later today. Event streaming, or data in motion, was first developed at LinkedIn by the founders of Confluent. As we often see, the very best open source technologies make their way from Silicon Valley into the enterprise. And as of today, over 70% of Fortune 500 companies use Apache Kafka, the majority of which are Confluent customers. Let's quickly discuss what we see happening around us every day, which is that data is changing the world. Whether through our interactions with mobile applications, seeing real-time metrics from recent SpaceX launches, seeing maintenance workers with tablets, or witnessing our doctors working with our digital medical records, our interactions with the world are immersed with data. Data is helping the world build rich front-end customer experiences. And this is important because even if your business has nothing in common with a company like Netflix, this is the type of experience that your customers expect in all aspects of their lives. Data is helping companies move towards real-time back-end operations. Amazon warehouses are a great example of how they've driven efficiency and speed through harnessing data. Confluent has the technology, experience, and support to make these type of outcomes possible for any organization anywhere in the world. Let's talk a bit more about Apache Kafka, the open source project that Confluent is built on top of. Outside of the code, Kafka is also about the community. These numbers really speak for themselves. The community loves Kafka, and Kafka loves them right back. For the non-Kafka nerds in the audience, us too, a KIP is a Kafka improvement proposal, which is used to submit propositions for major changes to open source Kafka. The strength of Kafka is not only its completeness as a streaming platform, but the ecosystem around it. Kafka is not an island. Fun fact, there are 1,000, that's right, that's 1000, more lines of code for integrations to Kafka than lines of code for Kafka itself. And Kafka is no small project. So how does Confluent fit into all of this? As I mentioned earlier, the founders of Confluent are the original creators of Apache Kafka. And the team here at Confluent has over 1 million hours of contributing to the Kafka open source code base and managing Kafka clusters at the largest scale. At this time, we have over 5,000 clusters running in Confluent Cloud. Our platform extends Apache Kafka to be a secure, enterprise-ready platform, and we help enterprises all around the world successfully deploy Kafka at scale and accelerate their time to market. Because of our success our customers have achieved, we've won several important awards, including Forbes 100 Best Cloud Companies, Morgan Stanley CTO Innovation Award, being inducted into JP Morgan Chase's Hall of Innovation, and Bank of America's Enterprise Innovation Award. The largest, most innovative organizations in the world are partnering with Confluent recognizing us as a key element of their success. For those of you who are familiar with Apache Kafka, I just wanted to quickly call out some differentiators. We'll be discussing most of these in detail later in the discussion, but I just at least wanted to prime all of you. We have a set of 130 plus pre-built connectors to help you easily connect your different data sources and sinks. We enable you to elastically scale, saving significant costs by avoiding manual scaling and provisioning. We offer an event streaming database, KSQLDB, which is the easiest way to build stream processing applications. We have a set of security functionality to ensure enterprise-grade security. And last, we have a set of functionality that enables you to increase your operational efficiency while keeping costs low. Excuse me. Catch my breath. I'm so verbose. Before we get into our discussion of the edge, I would like to discuss another important differentiator that deserves its own slide, and it's really kind of the basis of our demo today, is that Confluent empowers you to run everywhere, and I do mean everywhere. From a Raspberry Pi to a monster bare metal machine, Confluent works. Our customers can choose between a fully managed cloud product in AWS and a software product they can run themselves in their own data centers or VPCs, and of course you can use both. You can interconnect these into a global central nervous system for data in motion. And this is becoming a critical component of the cloud migration strategy of many of our largest customers because it allows their new applications to connect their input and output data back into existing legacy systems without requiring a big migration all at once. Both Confluent Cloud and Confluent Platform are subscription services where the spend scales with usage, so you're only paying for what you use. I think a lot of people think of a journey to the cloud as lifting and shifting VMs or instances. That just kind of takes your debt from your on-prem into the cloud, your tech debt. So by replicating your data from on-prem into the cloud, you can build out brand new applications with that replicated data set. And then once you're satisfied with your new applications, you can point your on-prem sources to the cloud. We see customers do it all the time. So what is the edge or edge computing? Wikipedia says, everyone starts with Wikipedia's definition, right? Wikipedia says, edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. From a practical perspective, the edge is really the closest you can get to your workload. That might mean an end user interacting with a mobile application or a weather measurement station in a remote area with no network connectivity. The edge might also be a combination of these use cases. Consider a travel platform, which will have events from mobile devices, events from the food inventory systems, updates to travel information, manifest, and loyalty systems. Even at the edge, having all this data in a single place or system has tremendous potential for enhanced customer experiences. Let's discuss the first of three common edge patterns. The first pattern is remote locations, which takes very different forms depending on your type of business. For a retail company, this may include warehouses, storefronts, kiosks, pop-up shops. For a service-oriented business, this may include offices around the world, right? Your remote locations. For logistics may include truck depots, maintenance shops, and regional offices. The next pattern is partially disconnected edge. This is a situation where the network connectivity is limited or time-bound. Think of a train entering a tunnel that relies on satellite communication. And for the duration of that tunnel, connectivity to the rest of the world is severed. Often, with these patterns, we see mechanisms in place to synchronize data once network connectivity is restored. The final pattern we'll be focusing on will be the focus of our demonstration later today. It's a new type of edge pattern. MEC, or multi-access edge computing, allows you to provide computational resources over telco or carrier networks, allowing you to service many devices using the same infrastructure securely and with low latency. There are also private MEC scenarios, we saw that announced yesterday, where 4G, 5G connectivity and edge computing resources can be provided to a specific customer and location where cell phone towers may not even exist today. So the edge is really cool, and it allows you to unlock new experiences for customers, gain insight from data points never previously available, or at least not in a timely fashion, or aggregate data from across the globe. The problem is the edge is difficult. The first and maybe the most important challenge is that of limited resources at the edge. Likely, the first thing that jumps to mind is budget, which is certainly part of the issue, but not the only limiting factor. At the edge, we often have little or no technical hands-on staff. In a retail scenario, this often means asking a retail associate to physically access equipment. I've been there before. At a remote monitoring station, there may be no one on site for days, weeks, or even months at a time. Change operations at the edge can feel perilous. Due to the aforementioned limited budgets and lack of hands-on support, often rollouts, upgrades, or changes at the edge can be overwhelming. Outages in any form in today's world generally result in a loss of confidence to end users of those systems, whether they're internal or external to the organization. Our second challenge is with device integration. Consider just a single department in a hospital. There are devices with different connectivity types, operating systems, manufacturers, etc. Getting these devices to communicate with a single messaging backbone can be very difficult. In this example, we're only looking at one department. Imagine the number of data points across the entire hospital, a network of hospitals, etc. AWS has this concept of well-architected framework, which distills what Amazon and AWS have learned over years of building robust, scalable systems. One of the tenets of well-architected is to loosely couple your applications, which means not having one thing talk to another directly because that is brittle and does not scale well. Instead, have something in the middle that scales really well and is highly available. Later in the presentation, we'll go over some of the technologies that Confluent has layered on top of Apache Kafka, which by its design is highly available and scalable. Think about how these features can help you build a global network of loosely coupled data consumers and producers. With our client libraries and connectors, we significantly reduce the burden of this design, and remember that we can run this anywhere, giving you a standard pattern that you can use globally. Finally, processing at the edge is no joke. You can certainly get connectivity between locations around the world. However, trying to process all this data in the cloud or a primary data center can drive up transfer costs and potentially delay insights just due to the sheer volume of data. By having systems at the edge that can provide some type of processing, think of aggregating or merging data, filtering events, or serving an embedded machine learning model, having a processing system at the edge is non-trivial, but extremely beneficial. Also, if you are looking at this diagram and you say to yourself, I've never heard of core near edge, that's okay, I'm pretty sure I made that up. Because during the demo today, I'll explain what I meant. There's things that sit near the edge, but there's also things that sit even further to the edge, and I think it's a good way to disambiguate them. So for the aforementioned difficulties, especially limited resources, we can look to the suite of AWS Edge services. AWS can help deliver compute options that address all the different edge types we discussed previously. Let's go through each in a bit more detail. AWS Outposts is a fully managed service that offers the same AWS infrastructure, AWS services, APIs, and tools to virtually any data center, colo, or on-premise facility for a truly consistent hybrid experience. AWS Outposts is ideal for workloads that require low latency access to on-prem systems, local data processing, data residency, and migration of applications with local system interdependencies. Outposts is available as a 42U rack that could scale from 1 to 96 racks to create a pool of compute and storage capacity. Coming soon, if not already, Outposts will be available in 2 smaller form factors, a 1U and 2U rack mountable servers for locations with limited space or capacity requirements. So think about those remote locations we discussed previously. These small form factor Outposts would be extremely helpful. AWS local zones are a type of AWS infrastructure deployed that places AWS compute, storage, database, and other select services close to a large population, industry, or IT centers. With AWS local zones, you can easily run applications that need single-digit millisecond latency closer to end users in a specific geography. AWS local zones are ideal for use cases such as media and entertainment content creation, real-time gaming, live video streaming, and machine learning inference. This is also another service when thinking about remote locations, especially if your use case permits data moving over the internet, albeit with much less hops. AWS Snowball, which is part of the AWS Snow family, is an edge computing, data migration, and edge storage device that comes in 2 different options. Snowball edge storage optimized devices provide both block storage and Amazon S3 compatible object storage and 40 vCPUs. They are well suited for local storage and large-scale data transfer. Snowball Edge Compute optimized devices provide 52 vCPUs, blocks in object storage, and an optional GPU for use cases like advanced machine learning and full motion video analysis in disconnected environments. You can use these devices for data collection, machine learning, and processing and storage in environments with intermittent connectivity like manufacturing, industrial, and transportation, or in extremely remote locations. Think military or maritime operations, before shipping them back to AWS. These devices may also be rack-mounted and clustered together to build larger temporary installations. I actually had a Snowball Edge at my house to ensure that we could run Confluent on it, which proved to be true. But let me tell you that when you power that thing on, you might as well call it an AWS avalanche for the first 15 seconds while this disk is spinning up. My primal fear definitely kicked in. It's quiet after that, though. The Snow family can help us address those partially disconnected or even fully disconnected edge scenarios. The final edge service we will cover is AWS Wavelength, which is an AWS infrastructure offering optimized for mobile edge computing applications. Remember that MEC? Wavelength zones are AWS infrastructure deployed that embeds AWS compute and storage services within communication service providers' data centers at the edge of the 5G network. So application traffic from 5G and 4G devices can reach application servers running in wavelength zone without leaving the telecommunication network. This avoids the latency that would often result from the application traffic having to traverse multiple hops across the internet to reach their destination, enabling customers to take full advantage of latency and bandwidth benefits offered by modern 5G networks. AWS Wavelength is available in multiple cities across the US on Verizon's 5G network, in Tokyo and Osaka, Japan on the KDDI 5G network, in Daejeon, South Korea on SK Telecom's 5G network, and in London on Vodafone's 5G network. So combining the power of AWS EC2 with robust carrier networks for cutting-edge, pun-intended use cases. So AWS helps us get compute and storage pretty much anywhere you need it when you combine all the services we just went through. What is missing, though, is a common platform that can easily be deployed across these services, that can scale to match your current and future workloads, and finally has mechanisms to connect the edge to the rest of your network. Of course, I'm talking about Confluent. By combining AWS services with our technology, we unlock the outcomes highlighted here. Migrations, global data meshes, universal data sharing, increased availability or providing DR, bridging your on-premise resources to the cloud, and of course, the most apt for this presentation, aggregating data from the edge. So I mentioned our technology that makes all this easier. So we're now going to dive deeper into what Confluent brings to the table. The first technology I'm really proud to discuss is Confluent for Kubernetes. Our engineers designed a truly kube-native way to deploy Confluent, and coupled with AWS EKS, we have an ideal architecture to deliver Confluent in a scalable, highly available manner supported by both AWS and Confluent. Also of important note, local zones, wavelength, and outposts all support EKS. Confluent for Kubernetes introduces a declarative API to deploy and manage Confluent in a variety of infrastructures. This means you can manage topics and securities through infrastructure as code, rather than manual processes. It also enables you to integrate with ecosystem toolings to get you cloud-native security, reliability, and DevOps automation. Let's expand on some of the benefits of Confluent for Kubernetes across three key differentiators. The first is cloud native. Confluent for Kubernetes allows you to quickly scale to changing business demands with a single command, elastic scaling, rather than more manual and time-intensive processes that you would typically need to use. It also helps accelerate time to value by simplifying the deployment and management of the platform through infrastructure as code approach that pre-configures everything. This means it provides an enterprise-ready platform that takes the guesswork out of deployment and management. In terms of how it's complete, it helps you implement use cases end-to-end with all of our Confluent platform components ready to use out of box. It is also secure by default and integrates with cloud-native Kubernetes ecosystem tooling like HashiCorp Vault or AWS Secrets Manager for managing secrets. Finally, it makes data in motion available everywhere because it provides a consistent operational experience across market-leading Kubernetes distributions. It also makes it easy to build hybrid and multi-cloud architectures by simplifying the process of connecting self-managed clusters to Confluent Cloud. This helps you get cloud ready and allows them to seamlessly migrate workloads to Confluent Cloud when you're ready in the future. Confluent for Kubernetes, or C4K or CFK for short, will give you a consistent, templatable, source-controlled mechanism for deployment of Confluent across the aforementioned suite of AWS Edge services. So Confluent for Kubernetes and AWS Edge services make it easy for us to get Confluent everywhere and anywhere we need it. Confluent cluster linking will help us put our data in motion and allow us to connect all of our sites, edge, regional, headquarters, etc., together to form a global data mesh. Data is syndicated and replicated between on-prem and on-prem, cloud and cloud, on-prem and cloud, edge and cloud, and any mix that fits your outcomes. All of this is achieved by leveraging the internal replication mechanism of Kafka and preserving offsets between source and mirror topics. Though not necessarily required for edge use cases, offset preservation is helpful for some multi-region cluster or DR scenarios. Okay, we got Confluent deployed everywhere, and we linked it all together. You're probably wondering, how do we actually get data in and out of the system? It's a pretty important question. Let's first discuss our supported clients. I'm sure that most of these listed up here support your use cases. However, I have no doubt that someone out there is laughing about your remote site running a Fortran application that was developed 20 years ago. We do have an answer for that, which we'll cover in the next couple slides. So in addition to this bevy of software clients, we also have REST and MQTT proxies, but now let's shift our focus over to Kafka Connect. Connect allows us to source events from other systems like relational databases or mainframes into Kafka topics, and we call those source connectors. We can also use sync connectors to take events from topics and send them into other data systems like Elasticsearch or S3. Finally, the Kafka Connect framework is fault tolerant and scalable. There are a number of popular open source connectors out there in the wild. However, Confluent has expanded on those open source Kafka connectors to further increase the number of available data sources. Data sources and sinks in order to move data in and out of Kafka. A developer working with open source Apache Kafka will have two options: develop their own connectors using the Kafka Connect framework, or leverage the aforementioned open source connectors already built by the community. The challenge with the first option is the time and effort it takes. In 2019, Confluent increased its connector portfolio from around 10 to over 100 supported connectors. Through this experience, we measured it takes an average of 6 weeks with a full-time engineer to develop one connector. And this is the time it took the world's Kafka experts. The challenge with the second option is that all of these open source connectors will be unsupported. This would generate significant risk for an organization deploying Kafka into production. What would happen if something breaks? Would the organization feel confident about fixing these issues without help from the experts? This is why Confluent offers a portfolio of over 130 connectors, around 100 of which were developed and supported directly by us, another around 30 which were developed by our partners and validated fully by Confluent. You can run these connectors yourself anywhere, including the edge, using Confluent Platform or fully managed on Confluent Cloud. Remember our client libraries and that Fortran application I joked about? If you do have a legacy system that cannot easily integrate with Kafka or Confluent, you can grab the events from the underlying database, mainframe, or messaging system using these source connectors. You can even scan log files on an application host and send those to Confluent using our connectors. Between our client libraries, our REST and MQTT proxies, and finally our connectors, we can bridge almost any data from anywhere to anywhere. Remember the challenge earlier of needing processing at the edge? Kafka Streams allows us to build out applications in either Java or Scala to do things with events in real time. You could, for example, filter out specific events from one topic using a stream and then place the subset of events into another topic. You could transform events from one topic, say change serialization or aggregating fields, then place them into another topic. You can even take events from multiple topics and combine them. Streams also supports embedded machine learning models. The problem with streams is that Java or Scala can be difficult and limit how many of our engineers would be able to develop streams. Fortunately, Confluent built ksqlDB on top of Kafka Streams to provide a lightweight SQL-like interface so we can build the same streaming applications without Java or Scala, like in the example above. What we see here in this slide is the same task being achieved using a Java application that's consuming events from Kafka and then coded in Java on Kafka Streams, and finally, a single select statement in ksqlDB. I think most of you will agree that this powerful abstraction layer will make data in motion applications much more accessible to your teams. As a matter of fact, if you want to learn more about ksqlDB and our connectors, please check out confluent.awsworkshop.io. So once you and your teams have all these awesome streaming applications running in ksqlDB, we have some tools that will make managing these applications even easier. The first is our Stream Catalog, which is a knowledge base for data in motion. It's like the company's public library for event streams. The key idea is to centralize all of the Confluent-related metadata from any of your clusters. With all that real-time processing we're going to do, it's important to determine where did this data come from, where is it going, and where or when or how was it transformed. This is what Stream Lineage does, providing a GUI to give us the answers to those exact questions. Finally, Stream Quality, via our schema registry, ensures that events have proper fields and field types, providing a mechanism for schema evolution without interruption, and in the near future will provide validation based on business rules. We have covered many of the tools that make it easier to get Confluent and data in motion running at the edge. However, the edge sort of implies that there's something in the middle, right? So sourcing and connecting all this data globally is one part of the picture. But eventually you're going to want to aggregate all of this, and you might need a pretty significantly sized cluster to hold all of that data. Kafka at that scale can be daunting. This is why Confluent Cloud, where Confluent Cloud comes in, which is our fully managed service in AWS. Let us at Confluent worry about all the operational burden so you can focus on building things instead of running them. A few Confluent Cloud features. Provision a cluster instantly. No waiting for a cluster to spin up or concern for large operational teams for large scale workloads. Usage-based billing. No need to spend a penny more than you have to. You will always be on the latest version of Kafka. Did we just upgrade your cluster with no downtime interruption or performance degradation? Yep, we did. With this massive global data mesh, you're going to want industry-leading support. Confluent can support clusters running anywhere at the largest scale. We also have some exciting new support features like Health Plus, which can provide you intelligent alerts that you can get in front of potential issues before they become problematic. We also offer proactive support, which allows our support teams to send out notifications of any probable trouble based on telemetry from your clusters. So we discussed all of the AWS and Confluent services, features, and technologies that make the edge easier, but to further cement the concept, let's discuss some use cases. In retail, digital transformation enables many new innovative use cases, including customer 360-degree experiences, cross-selling, and collaboration with partner vendors. This is relevant for any kind of retailer. No matter if you think about retail stores like Walmart, coffee shops like Starbucks, or cutting-edge shops like Amazon Go Store. National or global retailers can have hundreds or thousands of brick-and-mortar stores, which can generally have some type of on-premise compute and storage. Current infrastructure could be displaced by Outpost, local zones, or Wavelength running Confluent, which allows customers to aggregate the compute and potentially share data across locations. Less overhead, more possibilities. Consider logistics and edge use cases. Correlation of data in real time is a game changer for any logistics scenario. Track and trace end-to-end for package delivery, communication between delivery drones or humans using cars, and the local service collection booths. Accelerated processing in the logistics center, coordination and planning of car sharing / ride sharing, traffic-like management in a smart city, or so on. Think about a smart tractor or trailer communicating with a smart camera in a connected city that can alert the driver or safety system of oncoming traffic around a blind quarter. Got to be able to do that in low latency. With the low latency of Wavelength and data sharing potential of Confluent, we can unlock these type of real-time possibilities that were only dreams of the past. Industrial edge use cases include edge integration and processing in real time, which are key for success in modern IoT architectures. Various use cases exist for Industry 4.0, including predictive maintenance, quality assurance, process optimization, and cybersecurity. Building a digital twin with Confluent is one of the most frequent scenarios and a perfect fit for many use cases. The AWS Edge Suite with Confluent can help provide modern compute and data movement to industry. But I want to call out Private MEC for a moment. AWS can deliver an outpost to an industrial site, and in North America, Verizon can wire it for 4G, 5G connectivity, providing you a private wavelength zone. Layer on Confluent, and you have a private MEC infrastructure that can blanket your entire locale, help you modernize, replace legacy network equipment. This is by no means an exhaustive list of use cases. I had the pleasure of speaking with an Edge session hosted by Tapio Networks a few months back, where I had the chance to meet Chris Allen of Red 5 Pro. His company is using Wavelength to provide viewers of live events new, novel real-time interactions. For example, imagine attending an air show and being able to watch from the inside of the cockpit in near real time using Red 5 Pro. That's already happening today in Wavelength. So we've covered how edge services and Confluent technologies complement each other to create a global data mesh. However, I wanted to take a moment to highlight how our partnerships have grown. Back in August of 2020, we only had a single badge. A little over a year later, here we are, and we'll be adding Lambda and RDS service ready to the collection in the near future. So what is my point here? Confluent, in my opinion, has the best platform in the world for data movement. AWS, in my opinion, is the best cloud provider in the world. AWS is likely not going to dedicate the resources to build the technology we have, and Confluent is likely not going to start building data centers anytime soon. We truly are better together, which enhances the outcome we could jointly provide to you. So let me tell you an origin story. I think we all like origin stories. We are now going to dive into the Confluent Wavelength solution, which is the basis of our demonstration, and something I am really proud of. This all began with a call from a solution architect from the Wavelength team at AWS. They learned of Confluent through our Outpost Service Ready designation and found a blog post from a fellow coworker of mine, Kai Werner. Kai is one of our field CTOs, and he works with customers on their data in motion use cases on a daily basis. This solution architect drew our attention to one particular diagram. This diagram shows Kafka collecting events at the edge and then replicating the events running in a factory, then aggregating in the cloud. The question was, can we replace the edge in factory clusters with Wavelength? My answer was in the form of a quick diagram and a ton of enthusiasm to figure out if we can actually make this work. And this is what we came up with. Confluent running on EKS in Wavelength Zone, deployed using Confluent for Kubernetes. Our edge cluster is then cluster linked to an aggregation cluster in the AWS region. This particular diagram shows an industrial use case centered around predictive maintenance. Remember, we can run embedded ML models in Confluent, and with the low latency of Wavelength, we can provide predictive failure notification in a timely manner. What about aggregation, though? What does this potentially unlock? This is a story I love. So this is ultimately the big picture. We have multiple sites using clusters and embedded ML models at the edge, with the full data set across all locations being aggregated into Confluent Cloud using cluster linking. This would allow us to take our aggregate data set, sync it into S3 using a fully managed connector, and then further train our ML model using Amazon SageMaker. As our model improves in its ability, we can then push down the updated model to the edge. We create this self-fulfilling loop of improvement while simultaneously removing operational burden from the actual factory site. Awesome. So now, I gotta turn this on real quick. So now it's time for me to put my data where my mouth is. We have a powerhouse of logos on this slide. You turn it over a little too soon. Can you go back real quick? We have a powerhouse of logos on the slide, which all contributed to the demo today. Interestingly enough, Confluent, Hivecell, Verizon, and AWS are all partners with each other as it pertains to this solution. So let's jump right into the demo. Afterwards, Justin will walk us through the data path of what you're seeing. All right. So what you see here is a quick visualization. I'm going to play some music. It's happening in real time. I didn't fake this. So let me just stop real quick. And Justin's going to explain exactly what's happening. So can we give Justin just a quick round of applause? Because one, he deserves it, and two, it's part of the demo.
How's it going?
Oh, you switched it back.
Oh, you should.
Don't switch it back.
I messed it up. I'm sorry.
You messed it up. It's okay. That was your clapping right there, by the way. All right, go ahead.
Right, so this is what we have. We have here on the stage a Hive cell. And the Hive cell is basically a portable Kubernetes cluster that, in this case, is connected to the 5G network, right? So we have effectively a 5G antenna connected from the Hive cell up to the Verizon wavelength zone. We have a wavelength zone where we are running Confluent Platform using Confluent for Kubernetes. This is our this is our Confluent solution for running on edge. Right? So what we have is we have the speaker, which is playing music, connected to a Raspberry Pi with a sound detector. Mm-hmm. that is wired up to the
Right. So what's happening is the loudness sensor is detecting the music and generating MQTT events. Those MQTT events are hitting Confluent Platform running in wavelength zone. And we actually have a wavelength zone here in Las Vegas, right here in Sin City. If you want to pick it up from there.
Yeah.
Yeah.
We have a wavelength zone running in Las Vegas. We have Confluent Platform running on the wavelength zone using automation that Joe and I built. Mm-hmm. And that is cluster linking up to Confluent Cloud. So we are able to collect data from this Raspberry Pi, send it via an MQTT proxy running on the Hive cell up to the Confluent Platform instance running in wavelength, and then we're cluster linking that data up to the Confluent Cloud. This allows us to have compute at the edge, right, where we're gathering all the information, gathering this telemetry data from various services or from various components, and then aggregate that up into the cloud. Once it's in the cloud, we then are able to sync it out to a Postgres database, in this case Amazon RDS, and from there we're displaying it in Grafana. So altogether, this allows us to put an end-to-end solution where we have data coming from remote sites, potentially, in this case, a stage, but maybe your factory, maybe your store, aggregate it all together and analyze that in real time in the cloud.
Perfect. Thank you so much, Justin. And just to show everyone that again, just because we cut it so quickly, we're not faking it. You start playing music, it will visualize. And if I stop it, it'll stop, right? So you can see this is a very novel example. But the reality is this is an MQTT proxy running here right now. So I could take this, we could plug it into any of your networks, start pointing your MQTT devices at it, and start getting data in motion right away. You could also run full-blown Confluent Platform here. So if you had a scenario where you're like, I cannot lose any data, you can have a full persistence layer here at the edge, and then once your connectivity is restored, cluster linking will pick up, move all that data right away. We actually have people running in the field with Raspberry Pis, running Confluent Platform, pulling metrics from from all their equipment, and then once they get back to home base, cluster linking helps bring all that data and then make it useful to the rest of the organization. So let's switch back to our PC. Oh, fantastic. All right, so actually I just want to give a couple quick shout outs. So I wanted to call out Robbie Belson he's an edge evangelist at Verizon. Robbie and Justin right here helped me fully automate this so you can quickly run a POC for yourself. Also, I'd like to thank HiveCell for building the prototype Verge, which is sitting right on top here, for today's demonstration. So, quick thank you, but also I think we have enough time if anyone has any questions. So, any questions out there? I don't see any hands. Am I missing it?
One quick note, the code for the demo today,
Oh, yes. Thank you.
it lives on GitHub, so you can actually do this today. You can go to github.com/Verizon/5G Edge Tutorials and provision a wavelength cluster running or an EKS cluster running in a wavelength with Confluent Platform running on top of it. So this is fully doable today. You can go home and set this up or test it.
Fantastic. So, the session doesn't officially end for another 10 minutes or so. So if you do think of any other questions, we're going to stick around. But we thank you so much for your time. We really appreciate it. Thank you, everyone.
Yeah. Go ahead.
Oh, that's a great question. So we're using what's called source-based cluster linking. So there are two flavors of cluster linking. Destination-based cluster linking, where the destination cluster will monitor the source cluster and pull data into it, or source-based. We're using source-based in this scenario. So our CP cluster, oh, I'm sorry, real quick. The question was, where's cluster linking running? Our CP cluster running in wavelength zone is source-based cluster link to Confluent Cloud, and it is pushing events up to the Confluent Cloud cluster. So when it detects any type of severance of connectivity, it just kicks up where it left off. It knows all its offsets, and it just starts pushing data as soon as it's up and running again. Great question.
The idea here is that you can run Confluent clusters wherever you want, or you can run them on wavelength, you can run them on the Hive cell, although we're not doing that today. You can run it in your data center, you can run it on an outpost, and then you can use cluster linking to aggregate all of the data up into a Confluent Cloud cluster, a fully managed Confluent instance, and then do your processing there.
That's great. We have another question over here.
So is that Kafka messaging at the heart of this thing?
Absolutely. So the question was, is it Kafka at the heart of it? And that's exactly what it is. So Confluent platform is Kafka in the core of things, but we layer on some technologies that make it more enterprise ready. And of course, we can throw in all the support, professional services, and all the other things you want to do to build, gigantic Kafka scale. Great question. Any other questions out here?
From a data validation standpoint, I mean, you have ways built in that kind of handle, when we have the same thing getting updated in different places, and then there's conflicts.
Oh, that's interesting. Okay, so the question is, do we have validation if there were conflicts, if we had multiple things like cluster linked? Is that what we're talking about? Like two different, it's a great question. So it doesn't exist today, but by either the end of the year or by Q1, we'll have a scenario. In that scenario, what we would do is we would cluster link two different things, and we would make sure the topic names were different. So on the aggregation cluster, both topics would exist, but they would only exist, one would exist on the edge, different ones. However, with cluster linking, we're going to have two new features in the future. One's going to allow you to have the same topic name in all your edge sites, but then add a prefix based on the cluster link name, so that input topic is input topic at anywhere at the edge, but it is Houston-input topic when it cluster links. And then the next step is to add a funnel type of scenario where we can take all the quote-unquote input topics, regardless of where they're coming from, and then combine them into one aggregate cluster. That's going to come out later next year. Great question. Any others? I could talk about Kafka all day. Oh, we didn't really talk about we didn't really talk about the latency here. That's an excellent question. So the question was, what is some of the latency here? So right there fortunately, there's a wavelength zone in Sin City, which made this demo possible. If there wasn't one here, I wouldn't have done it. But between the Verge, Hive cell setup, and Confluent Platform wavelength, we're talking about 20 to 30 milliseconds of latency, which is actually really impressive if you think about it. I'm a network engineer by heart, so if we had two devices on the same wavelength zone and they were peer-to-peer, you're talking about 20 to 40 milliseconds. Like, you could real game first-person shoot with that, right? But then from Confluent Platform to Confluent Cloud, we're riding the Verizon to AWS backbone. That's about 40 to 50 milliseconds to get from Las Vegas over to US West 2 in Oregon. At that point, Confluent the cluster linking, very minimal overhead. You're talking about extra millisecond or two. Really, it's the network path. That's most of your latency. Then syncing in RDS is almost instantaneous, less than a millisecond. And then Grafana, reading from it is almost near real time. Actually, it probably takes us longer to pull Grafana from Oregon and get it back here than it does to actually get the data there. Great question. Yes, we got a question right here.
Are there any plans, and maybe this isn't the right forum for it, but are there any plans to extend the management of Confluent through Terraform?
Oh, we actually have an official Terraform provider now, right?
It's early access.
It's early access, sorry about that. So yeah, you can absolutely do all of this with Terraform in the near future.
Are you referring to, so the question was, are there plans to extend the management of Confluent through Terraform? Quick clarification, are you referring to the managed Confluent Cloud solution or the self? Yeah. Okay, yeah. The APIs for that are out now, and the Terraform provider is early access.
Is that as a reInvent?
It was like a month ago, a couple weeks ago?
Yeah, it's in progress. We can chat after on the state.
Yeah, absolutely. Any others out there? I've got a question right here.
Can you talk a little bit more about the Raspberry Pi?
Oh, Absolutely. So the question was around the Raspberry Pi and what we're doing here. So again, I wanted to come up with a novel example that would be easy to demo here in this space. So what we have is we have a little loudness sensor. It's a little IoT device. It's kind of hard to see, but it's right here above the speaker. And what it's doing is it's taking just a general relative, giving us like an integer value from 0 to 400 with the relative loudness. So the loudness would be 400, the lowest is 0. It's, you can hear a pin drop. And what I have is running just a very simple for loop, running in Python. I'm not a developer. And every 150 milliseconds, I'm pulling the value from that sensor, and I'm generating an MQTT event. The MQTT event is hitting the MQTT proxy that's running here on the Hive cells, and that MQTT proxy is using that Confluent platform in Wavelength Zone as its backend. So as soon as it receives a message, all it knows how to do is produce into some Kafka cluster, and it's producing into Confluent platform running a Wavelength. Very good question. But the idea, though, is that it doesn't have to be a novel example, right? It could be full-blown. You could have a full-blown IoT shop and take the stack, get the IP configured right? And then take your existing IP for your MQTT proxy or change your DNS, and you could be using this right now.
One of the stories we're looking at today is the idea of collecting telemetry data from airplanes as they fly, through the air, right? And then once the airplane lands, at an airport, we're going to gather the telemetry data from the airplanes, feed that through either a Hive cell or an outpost or through a Wavelength Zone, and analyze that to determine basically engine health or motor health or health of whether this airplane should be back in the air.
Yeah, excellent point. Any other questions out there? Oh, that's actually a great question. So there is some work to build some automation out so that if you were traversing between wavelength zones, so let's say you're leaving, your truck is leaving New York City, right, and you're heading towards Atlanta, and I'm picking on those because those are 2 wavelength zones. And as you start to approach Atlanta, you want to connect because you want the lowest latency. There is a service discovery from Verizon out there that you can enable and put your clients on that will help you figure out to break up that pattern. So the service discovery, the client can reach out to service discovery, say, hey, is this the closest wavelength zone to me? No. And I can then switch over to a new cluster. And because of cluster linking, it doesn't matter what I'm producing to, we can all send it back to the aggregation. There's even some automation, it's a little far out, that we could dynamically provision Confluent Platform as you approach Atlanta to spin up clusters on demand. So you can make it really like self-service to the point where you're not running Confluent Platform in Wavelength Zone for no reason, you run it as needed. We've done some experimentation with that, and we're really happy with, or at least our initial results. Any other questions out there? Absolutely. So the question is about encryption. Could we encrypt? So there are a couple pieces to that. So there is a Connect cluster that we put there. It actually isn't necessarily used in the form of this demo, but you could, if we were running a full-blown MQTT server here, we have a source connector that can pull MQTT and would work just this way. Instead of pushing the data, which we're doing now, we could pull it. But that doesn't really address your question about encryption. So absolutely, Confluent Cloud and Confluent Platform support TLS. They support encryption at rest. In fact, Confluent Cloud clusters, by default, they're encrypted. You can't have a non-encrypted data at rest Confluent Cloud cluster. It just doesn't exist. We even have a solution for encrypting before you produce messages. So we have client libraries and we have some accelerators around the whole idea of encrypting the message, then producing it to Kafka, and then consuming it and then decrypting it. So you could absolutely be ensured there's nobody reading that data but you. Great question. Any others out there? All right. I think we've exhausted the audience. I appreciate you guys.
Thank you very much for coming.
Thank you so much.
Appreciate your time. And let us know if you have any questions after this.
We're at booth 220, Confluent, Data in Motion. Check us out.